This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2018 AP Calculus exam, free response question AB1 BC1, namely the table of values method or the candidates test. My name is Steve Kokoska. I'm a professor at Bloomsburg University of Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll begin by briefly reviewing some relevant definitions involving absolute and relative extrema and critical values. Then I'll review a few relevant theorems, including the extreme value theorem and Fermats Theorem. Then I'll present the table of values method. And finally, I'll try a few examples. Some of the most important applications of differential calculus are contextual optimization problems. And we see a lot of these types of problems on the AP Calculus exam. And in these problems, we need to find the optimal or the best way of doing something. Well, more mathematically, these problems involve finding the maximum or minimum values of a function. To begin this study, we need to consider the definitions of maximum and minimum values. Now, I'm not going to read through this entire definition. Let C be a number in the domain D of a function f. The function f has an absolute maximum at C if f of C is greater than or equal to f of x for all x in the domain D. The number f of C is called the absolute maximum or the absolute maximum value of f on D. And there's a similar definition here for absolute minimum. Here's just a little bit more terminology associated with this definition. An absolute maximum or minimum value is also called a global maximum or minimum value. And the maximum and minimum values of f are also called in general extreme values of f. Now, it's possible for a function to have a largest value in a neighborhood, not globally. So here are a few more important definitions. The function f has a local or relative maximum at C if there exists an open interval I containing C such that f of C is greater than or equal to f of x for all x in that interval I. And that means that f of C is greater than or equal to f of x whenever x is near C. The number f of C is called a local or a relative maximum value. And there's a similar definition here for a local or relative minimum value. Here are a few notes related to this definition. The concept of a neighborhood of C, or near C, means an open interval containing C. In general, a neighborhood does not need to be a symmetric open interval about C. And it's certainly possible for a value f of C to be both an absolute and local extreme value. A function cannot have a local maximum or a local minimum at an endpoint. If C is an endpoint of the domain, we cannot form an open interval I containing C such that all values in the interval I on both sides of C are in the domain. But it is possible for a function to have an absolute maximum or absolute minimum at an endpoint. And of course, some functions have extreme values and some do not. So it would be nice to have some conditions under which a function is guaranteed to have extreme values, so that I'm not searching in vain. The extreme value theorem gives us some conditions under which a function is guaranteed to have extreme values. It says that if a function is continuous on a closed interval a to b, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d in the interval a to b. Here's a closer look at this theorem. An extreme value may occur at more than one place in the closed interval. Both conditions, continuity and a closed interval, are necessary. If either one is not satisfied, then absolute extreme values are not guaranteed. Now, they may exist, but we can't say for sure. And the extreme value theorem is an existence theorem. It guarantees the existence of the extreme values. So now the question is, where do we look? For a differentiable function, the tangent lines are horizontal at the local maximum and minimum points, and each line has slope 0. Therefore, f prime is 0 at these points. Fermats Theorem says this is always true for differentiable functions. It says if f has a local maximum or minimum at c, and if f prime of c exists, then f prime of c is equal to 0. Here's a closer look at this theorem. First, the contrapositive is of course true. If f prime of c exists and f prime of c is not equal to 0, then f of c is not a local extreme value. If f prime of c is equal to 0, we are not guaranteed that f of c is a local extreme value. This is a common error on the AP Calculus exams. And it seems unreasonable to expect to find all local extreme values at places where the derivative is 0. It seems like we need to look in other places also. Just thinking about the absolute value function, we need to consider places where the derivative does not exist. So, Fermat's theorem and a few simple examples suggest that we should at least start looking for extreme values of a function at the number c where f prime of c is equal to 0, or where f prime of c does not exist. And these numbers have a special name. A critical number of a function f is a number c in the domain of f, such that f prime of c is equal to 0, or f prime of c does not exist, and I abbreviate that as DNE. Here are a few notes about this definition. First, a critical number is also called the critical point, or a critical value. Now, I think the word number makes it clear that they are x values and not points in the plane. However, the term critical point is consistent and traditional, and it's used on the AP Calculus exam in both questions and solutions. Finally, we can conclude from all of these definitions and theorems: if f has a local maximum or minimum at c, then c is a critical number of f. Finally, here's a statement of the closed interval or table of values method. In order to find the absolute maximum and minimum values of a continuous function f on a closed interval a to b, first find the values of f at the critical numbers of f in the open interval a to b, find the values of f at the endpoints of the interval, and then the largest of the values from these two steps is the absolute maximum value, and the smallest of these is the absolute minimum value. This is also called the candidates test, and I think this is a very prescriptive and straightforward method for finding absolute extreme values. If the conditions are satisfied, just create a table of values and find the smallest and largest numbers in the table. Let's try an example. Find the absolute maximum and minimum values of the function f on the interval -2 to 4. Well, the function f is continuous, it's a polynomial, and the interval is closed. So we can use the table of values method. I'll start by finding the critical values. Here's the derivative of f, and I need to check two places. First, where the derivative is 0, and I found two values, x equal -1 and x equal 2, and where the derivative does not exist, and in this case there are no places where the first derivative does not exist. So there are two critical values, and both lie in the interval -2 to 4. So I'm ready to construct a table of values. Here's a table of values with all the relevant critical numbers and endpoints. The absolute maximum value is 33, and it occurs at x equals 4. The absolute minimum value is minus 19, and it occurs at x equals 2. Here's how I can use technology to help solve this problem. On a TI-Nspire calculator page, I first defined the function f. I used the solve command to find the values of x where the derivative is 0. Since f is a polynomial, I know there are no places where the first derivative does not exist. And I used a lists and spreadsheet page to create a table of values. It's now pretty easy to pick out the absolute maximum and the absolute minimum values. Here's a graph to visualize this solution. This shows the graph of f with all the important points labeled. I can see the absolute maximum and the absolute minimum values. But remember, this graph only confirms all of my calculus results. It isn't a substitute for the analytical work. Here's one more example in context. The rate at which water is released from a spillway is modeled by the function r for t between 0 and 3. In part A, how fast is the water being released at time t equal 2 hours? And in B, find the coordinates of all the local extrema on the graph of r and indicate whether they are local maximum or local minimum. And in C, find the absolute maximum and the absolute minimum release rates over the given interval. Now I think this is a pretty good AP Calculus type question, and I'm going to leave parts A and B to you. So let's consider part C. First, R is continuous on a closed interval, so I can use the table of values method. I need to find the critical numbers, so I found the first derivative. Now I need to solve the equation r prime of t equals 0, but I couldn't solve this analytically. So I used technology to find these two critical numbers. And r is differentiable on the open interval. Well, it's differentiable everywhere. So there are no places where the first derivative does not exist. Here's how I used technology to solve this problem. I first defined the function r, and then I used the zeros command to find the critical values. I used this command so that the results would be stored in a list, and I can then refer to specific values in this list. And here's a graph of the function r with the critical points labeled. Here is a lists and spreadsheet page with all the relevant values. Well, here's a table of values. And using this table, here's a summary of my results. I hope this video provides some insight into the table of values method, a few calculus-type problems, and the use of technology to solve and visualize these types of problems. And just a reminder, there are lots of valuable resources on the TI website. There's material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.